Howdy, everyone. I hope that you're doing well. My name is Andrew Timming, and I am a professor of management. And I'm the author of this textbook, Applied Statistics, Business and Management Research. And I want to welcome you to the second part of my lecture series on multiple regression analysis. Needless to say, if you haven't watched part one of this lecture, I would urge you to stop and go back to part one. If you have watched part one, that's great. You should be able to follow through with some of the concepts that I'm analyzing in this lecture. So in this lecture, we will extend some of the knowledge that you've gained on multiple regression and go a little bit deeper to what you learned from part one. All right, let's do this. Here you can see the textbook that we're using in this course, and as part of this lecture series, it's entitled Applied Statistics, Business and Management Research, and it was written by me. I hope you enjoy reading it. You are obviously most welcome to purchase a copy of it if you like from any major bookseller, or alternatively, if you'd like, you can go down to your local university library and ask them to get a copy. Now, when building multiple regression models, there are two different ways that you can go about doing this. You can build what we call confirmatory regression models, but you can also build what we call exploratory regression models. And I'll explain to you the difference between these two models now. But let me preface this by saying that generally speaking, confirmatory models are the best way to go. Uh, some people find exploratory model building to be akin to almost cheating. It's not cheating, but it's a sneaky way of building a uh, good fitting model. So, ceteris paribus, that is to say, all else being equal, you should opt for confirmatory models over exploratory models. So, what are these? Confirmatory multiple regression models involves variables that are chosen entirely on the basis of theory. So you look at the literature and you think about what types of variables, independent variables, might be associated with your outcome. And on the basis of that, you include those variables in your theory, in your model. Now, the overall model and the predictors, the independent variables, can be confirmed or they can be disconfirmed. Either way, it's good for science because you learn something whether your hypotheses are confirmed or disconfirmed. Exploratory model building, on the other hand, builds a model across a series of steps. So rather than building one model and testing it, it goes through a set of iterations. And during these different iterations, what happens is that independent variables or predictors that have weak correlations with the outcome get dropped out in the process. You can use statistical software, including SPSS, the one that we're using, to do this. So there's stepwise options, forward options, and backward options. And what these do is they run multiple models to explore which model produces the best fit in the final analysis. So when you do forward explanation, the model will add variables one at a time, and if a variable doesn't add value, it drops. And using backward exploration, all the variables are included in the first instance, and then it drops them one at a time to see how that impacts the model fit. As I said in the previous lecture, the advantage of using multiple regression over simple regression is that multiple regression can capture simultaneously the impacts of individual predictors on the outcome whilst holding constant the influence or the impact of the other predictors in the model. This is why we use multiple regression rather than running a series of simple regression models. So a control variable, also commonly referred to as a covariate, is one of the other independent variables in your equation whose value is being held constant, whose influence is being parceled out so that you can get an understanding of the pure effect of your independent variable of choice on your dependent variable. So let's just go through an example here of why it's important to have control variables. Let's say we want to evaluate the relationship between education and income, right? We assume that there's a positive relationship here, that as education goes up, income also goes up, right? Now that may very well be the case, but the fact of the matter is there's any number of other factors beyond income, or sorry, beyond years of education that also impact on income, right? So other factors might include your age. There might be a positive relationship between age and income, your IQ, your conscientiousness, etc. Now the advantage of multiple regression, if you have multiple predictors, is that allows you to measure the pure value of your variable of interest, in this case education, on income whilst holding constant the other control variables in your equation. So it's important to have control variables built into your equation because this reduces the risk of what we call omitted variable bias. Now, before running your multiple regression analysis, it might make sense to look for what are commonly referred to as multivariate outliers. These can present problems in terms of your analysis and your ability to generalize from your sample to your population. So as a form of what you might call a diagnostic test, you might want to look for multivariate outliers before running your model. So multiple regression is, as you already know, a parametric test. It is predicated on a normal distribution, on a bell curve, and therefore it relies on a meaningful mean and standard deviation and the concept of the normal distribution. Now there may be individual outliers that stand out. So in a particular variable, there may be very extremely high cases, say above 3 standard deviations or below -3 standard deviations, and you can obviously deal with those by either cutting them off or Winsorizing them. But you should also have a look for what are called multivariate outliers, and I give you an example here with the data in front of you. So it may be perfectly reasonable for a company to have 15 employees. It may be perfectly reasonable for a company to have 50 employees, and it may be perfectly reasonable for a company to have 20,000 employees, right? It also may be perfectly reasonable for a company to have $500 million in revenue. It may be reasonable for a company to have $1,650,000 in revenue, as well as perfectly reasonable for a company to have $660 million in revenue. But if you look at these three companies, you can see that there's one company that has 15 employees and $500 million of revenue. Now that combination seems a bit unusual, and we would call that a multivariate outlier. And it's possible that after investigation, you find that that 15 actually should be 15,000 and not 15. So maybe there was a data entry error. One of the most common ways of identifying multivariate outliers is through a test called Mahalanobis's distance, which will show you or identify potential multivariate outliers for you to double check before you run your analyses. Hopefully you remember from our previous chapter, from chapter 8, where we looked at simple regression, the concept of the coefficient of determination. Right? So just to give you a brief review, regression analysis uses what we call a ordinary least squares method to minimize the amount of error in your model. And with bivariate simple regression, when you're only looking at one x variable and one y, what we do is we fit a line of best fit within our data points, typically in a scatter plot. And that line of best fit tries to minimize the distance, the overall distance between the data points and the line itself. And the distance that I'm referring to between the data points and the line of best fit is referred to as the residual or the error, so the error in your model. Now, the strength of this relationship, as we talked about previously in the last chapter, the strength of the relationship between x and y is reflected in a statistic or a coefficient called Pearson's R. And this coefficient is always between -1 and 1, where -1 indicates a perfect negative relationship and 1 indicates a perfect positive relationship. But you'll recall when we talked about the coefficient of determination that if we square the value of R, what we end up with is the amount of variation in y, in our dependent variable, that is explained by x, by our independent variable. So just to give you an example, if we get a Pearson's R value of 0.374 and we square 0.374, then we get a little r squared of 0.140. If we convert 0.140 into a percentage by multiplying that by 100, what that means is that in this case, our x variable explains 14% of the variation in y. A similar logic holds in multiple regression, as you'll learn about in the next slide. So the question we now ask is, how do we know if a multiple regression model is a good fit, right? How can we tell the overall fit of that multiple regression model with multiple independent variables? Now, multiple regression analysis employs essentially the same principles as in simple regression, except now instead of having one line of best fit, we're going to have multiple lines of best fit. And these will correspond to the multiple B coefficients or beta coefficients that we have in our model. And just as little r in the context of simple regression or bivariate regression describes the relationship between x and y, beta also describes the relationship between x and y in multiple regression in similar terms, that is to say, in standardized terms. R is always going to be a number between -1 and 1, and beta is always going to be a number between -1 and 1. And just as in the context of bivariate regression, r squared, little r squared, explains the amount of variation in y explained by x, the same is true of what we call big R squared or capital R squared in multiple regression. So an R squared, a big R squared in multiple regression, explains the amount of variation in y that is explained simultaneously by all of our independent variables combined. So R squared, that is to say big R squared or capital R squared, is what we call the coefficient of determination. And it's always a number between 0 and 1 that says something about the overall fit of your model. And naturally, the higher the value, the better your model fits. Now, one thing you need to be careful about when it comes to multiple regression analysis is the idea of overfitting your model. So what does it mean to overfit your model? Let me explain point by point what I mean by this concept. So as I previously explained to you, R squared, that is big R squared or capital R squared, is the most important statistic in terms of assessing the overall model fit in regression analysis. That R squared will tell you in concert, all of your x variables together, how much variation in your dependent variable they explain. But one of the problems with R squared is that if you want to, you can artificially inflate it, or you can artificially prop it up simply by adding extra independent variables into your equation. So you can add additional independent variables, and by doing so, by definition, statistically, your R squared value will increase, it will go up. And that's the case even if the variables you add are meaningless or not significantly related to your outcome. So an unscrupulous data scientist, in order to bolster an R squared value, a coefficient of determination, might add a bunch of variables that don't add much value overall to the model, but increase the R squared value. So instead of reporting R squared, many data scientists report what we call a adjusted R squared. The adjusted R squared is a statistic that has a built-in mechanism to correct for this type of artificial inflation. And it's important to report the adjusted R squared rather than the R squared because overfitted models tend to be unreliable. So just like in simple regression, where we have coefficients, these were described in the previous chapter as B and Pearson's R, where B is unstandardized and R is standardized. The same is true in multiple regression, right? So R squared, as we already discovered, is the most important statistic of overall fit, but we also can make predictions in multiple regression using B coefficients. These are unstandardized coefficients. And we can also make explanations in the context of multiple regression using instead beta coefficients, which are standardized like the Pearson's R coefficients. So just to put this into context, if there are 5 independent variables and 1 dependent variable in your model, then really there are 2 ways of expressing this equation. One way is using standardized coefficients, that would be betas, and another way would be using unstandardized coefficients. Those would be B coefficients. And each coefficient has a t statistic associated with it that's generated from a t-test, which you learned about in a previous chapter, as well as a corresponding p-value. And remember that when p is less than 0.05, then we assume that that relationship is statistically significant and can therefore be generalized from the sample to the wider population. Now, one problem with our coefficients, with our B weights or beta weights, is that these are just estimates based on sample data. Remember, we only have information about our sample data. We don't have information about our population. But we don't really care about the sample data. What we really care about is whether the results that we found in our sample generalize to that population. And the coefficients that result from our analyses are obviously grounded in the sample, not the population. So what we really want to do is get a sense of whether or not this relationship between x and y, or between various x variables and y, generalizes to the wider population. And one way we can do this with a greater degree of confidence is to use what we call confidence intervals surrounding the sample estimate of the coefficients. So typically what we do is we report confidence intervals with a lower bound and an upper bound around a 95% confidence. And what we say is that we are 95% sure that in the wider population, the true value of B is within this particular range. The last concept I want to talk to you about in relation to multiple regression in part 2 of this lecture series is the idea of multicollinearity. It's a big word. So what does it mean, multicollinearity? Now, in a perfect world, in an ideal world, none of your independent variables would be correlated with each other. And this way we can measure the pure impact of each x variable on y. But of course we don't live in a perfect world. X variables, your independent variables, may well be correlated with each other. Now, if collinearity of all x variables is assumed to be 0, that is to say perfect independence, again this is in a perfect world, then each variable that we add is additive to arrive at r squared. Similarly, if each variable that we add, x variable that we add into our equation, is perfectly correlated with each other, if there's a perfect correlation among our independent variables, then we end up with a situation called singularity. In other words, perfect multicollinearity. And when this happens, you're simply not able to perform a regression analysis because a regression analysis assumes that the independent variables are at least somewhat uncorrelated with each other. As I said, in reality, many of your independent variables will correlate with each other, and this presents a problem. When these variables are excessively correlated with each other, We call this problem multicollinearity. So let me give you an example of multicollinearity and show you how you can assess it, given that it is a problem in the context of multiple regression. So let's imagine for a moment that you want to use a standardized test as part of your employee selection program, but you're not sure which test is the best to use, which one best predicts employee performance or potential employee performance. So let's say you administer 3 tests, X1, X2, X3, to a set of employees. The first one is an IQ test, the second is a verbal reasoning test, and the third is a numerical reasoning test. And you look at their relationship simultaneously on performance reviews. The problem with this configuration of predictors is that IQ tests also use verbal and numerical reasoning. So what this means is that when you generate IQ scores, it's likely that those IQ scores will be highly correlated with the verbal reasoning test and the numerical reasoning test because they overlap with each other. And because they overlap, they sort of obscure the true associations. So in order to assess multicollinearity in multiple regression analysis, we can use something called the VIF, the variance inflation factor. And this is a statistical method that helps you identify variables that are excessively highly correlated. And when you do identify those variables, you can simply remove one of them to reduce the amount of collinearity. Okay, thank you very much for listening to this lecture, part 2 on multiple regression, and I look forward to catching up with you at part 3. Bye, everyone.